Hey guys, we're on part 3 of question 2 of the 2018 final. And in the last video we found the value of K star using this Euler equation. And this time we're going to find the value of C star using the law of accumulation of assets. So let's assume, in the steady state, K dot equals 0. So we can write 0 equals AK alpha minus delta K minus C to the 1 minus B. And just remember that if we need to do that in the test, it's production minus depreciation minus stuff we eat. And that's going to give you the change in assets over time. Okay, so we need to solve for we need to solve for C. So pretty easy, let's just isolate it and solve. So bring C to the other side, we'll have C 1 minus beta is equal to AK alpha minus delta K. And then again we're going to raise both sides to the 1 over 1 minus B. And that's nice because it's already in the positive form. We don't need to flip over anything. And hopefully you already see the answer is just C equals AK alpha minus delta K to the 1 over 1 minus B. So we have two critical values, and basically where these intersect, or these provide the point of intersection between the two dynamic equations we have here, between the C dot and the K dot equations. And the question asks us, does a steady state exist? Well, I have no idea. I guess it depends on the value of the parameters, and on a test, I guess what I would just do is kind of looking at these. We know that delta and rho, delta is greater than 0. Whoops, that says less than 0. Delta is greater than 0, and rho is greater than 0. So this denominator is not 0, definitely. Furthermore, we know that K is going to be positive, and we know that B is positive. That's given to us in the question. So this is non-zero, this is non-zero, and this is something. So really, we just have a bunch of positive values. A is greater than 0, alpha and A, everything's greater than 0. So if these are just compositions of positive values, it stands to reason that they're going to intersect at a positive value somewhere. So, I mean, you could take this K and plug it in, make this K star, and make this K star, and make this K star, and then you could make this C star, and then set them equal to each other. You'd have this big monstrous equation. We can write it out. You'd have 1 over 1 minus beta times the quantity A alpha, and then K star, which is alpha A over delta plus rho to the, it's going to be 1 over 1 minus alpha, and then that is itself to the power alpha minus 1 minus delta minus rho is equal to alpha times alpha A over delta plus rho to the 1 over 1 minus alpha minus delta times alpha A over delta plus rho to the 1 over 1 minus alpha. I'll get rid of this stuff. And then, where were we? We just did this one. So then minus C, which is AK alpha. Whoops, we'll plug in K star there as well. Alpha A divided by delta plus rho to the 1 over 1 minus alpha to the alpha minus, you see where this is going, minus delta. So this is a mess, and I wouldn't do this on the test unless I had like a ton of free time at the end. Instead, what I would just say is these are composites of positive parameters there's no division by 0, there's nothing funny going on. So this is going to intersect somewhere, and I would say that yes, a steady state exists. Because it's not asking you to say what is the steady state. What is the steady state would be, whatever bundle of parameters came out of this. Okay, what it does ask though is how would you check it? So the answer for that, if you remember, we did 2 classes on system stability, and I strongly recommend that everybody review it, because I really think there's going to be, if not the calculation of a simple system with some numbers, just like a simple linear algebra system, then at least a question like this: how would you check that it's stable? So the way we would check it was stable is we're going to define both of these equations. This one is going to be called f of, and it has 2 variables, k and c. We're going to call this guy g of k and c, just like we're back in algebra class. And to check system stability, we need to build a Jacobian matrix, which is going to be a matrix of all the partial derivatives of all of the functions in our system by each of their variables. So we have f, delta f, and then we have g. And then each of them is going to have 2 partial derivatives, one for each variable. This one will have delta k and delta c, and this one will have delta k and delta c. Okay, so we calculate those partial derivatives, we put them into this matrix. But what we really want to find is the eigenvalues of the system. And the way that we do that is to calculate the determinant of our Jacobian matrix minus lambda, which is just a variable, times, and I have 4x4 identity matrix. Okay, and from this determinant we will get a quadratic equation in terms of lambda. And depending on lambda, that will tell us if the system is stable or not. And there's going to be at least three cases. So the first case is if all lambda are less than 0, then the system is totally stable. If 1 lambda is greater than 0, then the system will be saddle point stable. And this is usually what the Ramsey model is. And then if all the lambdas are greater than 0, then the system is unstable and you're screwed. Now the last case is if lambda equals 0. And if lambda equals 0, you have a complex number case, and it's going to be inconclusive. It's hard to write on the bottom corner of this thing. But basically, a complex number it'll decompose into something like this: a plus bi. If this a part equals 0, so if the real part equals 0, then the system will be orbital stable. It will orbit the steady state. It'll never reach it, but it also won't blow up. So that's kind of an interesting thing to point out. So if she asks about checking system stability, this is the process. You want to build a Jacobian matrix of all the partial derivatives of both of these equations, taking the partial with respect to both of their inputs. Calculate the determinant of the Jacobian minus lambda times the identity, and then solve the quadratic equation for lambda, and then check the values. Yeah, so hopefully that helps. In the next video, we'll move on to the OLG question. See you there.